Right now, this unit, we will finish the paper in question 5, 3 parts again, and you must do 2 parts, okay? And I asked you to make choices here, and it was interesting the choices you made because, frankly, you know, they're 3 diverse topics, so you were able to pick from this, and there's less calculation in this one now. Okay, 5A states the following then. State Avogadro's law. Now, I've already alluded to the fact that there are only 4 gas laws on your syllabus. It's not unreasonable that you would be aware of all 4, okay? Avogadro's law, equal volumes of different gases under the same conditions of temperature and pressure contain the same number of particles. Here we go again. PV, T, and N. And equal volumes under the same conditions of temperature and pressure contain the same number of particles. So if they're the same temperature and pressure, their volumes and their particles are related. So if you have a big volume, you have more particles. If smaller volume, you have less particles if you're comparing 2 gases. And that's what they're looking for there, nothing more than that. What is an ideal gas? That's a definition. This is a gas which obeys all the assumptions of the kinetic theory. Okay, it's closest to ideal behavior, in other words, right? The assumptions of kinetic theory. Real gases only approximate the assumptions of kinetic theory, whereas real gases, ideal gas, obeys all the assumptions of kinetic theory. Under what conditions of temperature and pressure do real gases deviate from ideal behavior? And the answer to that is high temperature and low pressure. Okay? High temperature, low pressure. 2 gas samples, 2 identical containers. Okay, high pressure, lots of particles, lots of collisions. Okay, those particles have much more room to run around. They're nearly moving all the time because they have hardly any collisions. Okay, so they're in constant random motion. Okay, they have little effect on each other because there's so few particles there. Right, and all the assumptions adhere to that. So, okay, low pressure means less particles, right? Means more space, and they're the ones. And high temperature means traveling faster. The faster they travel, the less effect they have on each other. Okay, than if they're going slower, and that's effectively what they're after there. Nothing more than that. Now, try and use something concrete when you're relating to gases. Like, don't always be just trying to visualize. You have to have a sense of mechanical kind of structure of that, so that you have a better understanding of what you're dealing with there. Calculate using the ideal gas equation the volume of 20 grams of oxygen gas that 20 grams of oxygen gas will occupy at a temperature of 25 degrees. T equals 25 degrees Celsius, okay, and a pressure of, and the pressure is 20 kilopascals. 20 kilopascals, right? And you're asked that now. So here we go then. You're asked to calculate, using the ideal gas equation, the volume of that many grams, okay? So what do you have there then? You're looking for, in this instance, the temperature there is given to you, the pressure, the volume you're going to be looking for. PV equals nRT. And you're looking for the volume. So the volume is equal to nRT over P. nRT over P. Are you okay with that? And so do we have all those then? We do. Okay. R is equal to 8.31. 8.3 will do fine. And N, the number of particles. Now be careful. It is 20, they've given you, in this instance, 20 grams of oxygen. 20 grams of oxygen. How will you get 20 grams of oxygen? You divide grams to moles. Okay, that's the number of moles. 20 divided by 16. No. That's where tagging comes in now. That's where tagging comes in, okay? You have a number, you have a unit, and you have a tag. It's oxygen gas. So it's 32. That's a very common mistake now. Be very careful with that, because the whole thing will go off the rails over you, you know. That's very important. So that's the number of moles. They gave you 20 grams of it. The minute they mentioned the ideal gas equation anyway, you had to have 4 out of the 5. And you're looking for V in this case, so it's not so bad in that sense. I think you have to work with that. And that's basically how you get around that, okay? And so that comes out as 0.625 moles. Okay, now what about all the others? That must be converted to pascals. 20 1000 pascals, and that must be converted to Kelvin. 273, okay, 293, 298, 298 Kelvin. Will you be careful, please? Okay, will you be careful? Metric is everything. Pop the 4 of those numbers in there, okay, and you're going to get your volume, okay, and the volume came out to be, the volume comes out to be, in this instance, 0.0774. Are you okay with that? Calculate using the volume of the volume. Do you know the units? Meters cubed. If they had asked you, they didn't ask you here, but they could well have asked you to calculate the volume in litres. You have to convert that, but you'll be divided by 1,000. Will you be careful now, please? Okay, it could be litres or it could be centimetres cubed. You'd have to convert them to those. Be careful. But the unit coming out of that formula has to be metric before you do anything else. It has to be metric. And once it's metric, then you work the rest of the way, and that's it basically, right? So there's your answer. By the way, that's fine. There's nothing wrong with that as long as you know it's meters cubed. If you left out meters cubed, there'd be a serious mark deduction. The problem with these particular calculations now is they're not difficult, but when you make an error, it's a very costly error. So you would need to be particularly careful with them. And so that's for 25 marks. There was 12 marks for this last calculation. Please list data. Please make a list of the data first. Even if it doesn't need to be changed, make a list of it anyway. Be very careful there now. That's a very common mistake. Okay, that's a very common mistake. Dividing by 16 for oxygen. It's oxygen gas. It's a gas. Don't forget that. Okay, I'm going on to part B. Totally independent of everything we've done to date. I haven't any of this done with you, and you need to be aware of the implications of that. What is the colour of the light associated with the line emission spectrum of sodium? You were asked one earlier about copper, and it was green-blue. This one is yellow. There's 6 colours there altogether, you have to know, and yellow is the one, right? Explain how a line emission spectrum occurs. Now, what would they want there? They'd want an account, a description of this. And well, I'm not going to do this with you now, other than give you the points that you would develop. Okay, it's very important that you say some of the following things now. Now, all your work here is revolving around Bohr's atom. And Bohr has these shells around the atom, and the electrons occupy them. N equals 1, N equals 2, and N equals 3. And you'd start off by dealing with that now appropriately. Explain how a line emission spectrum occurs. Electrons reside in very exact locations around the nucleus called orbits or shells. Okay, called orbits or shells. They reside only on the lines and they can't be anywhere else, right? And when an atom is excited, meaning it gains, when the atom gains energy, it could gain energy by being heated, it could gain energy by an electrical voltage, it could gain it by pressure or whatever, okay? But it would gain energy. Having gained energy, the electrons would jump to an outer shell. And when they do that, the atom is unstable. So it stabilizes itself by coming back to its original shell, and in doing so gives out energy in the form of light. So what you'll be doing there to explain all of this is, that's an emission spectrum, a typical emission spectrum, with a few random coloured lines on it. That's the spectrum. Okay, and each of these lines has an energy of epsilon, a rounded E, epsilon, okay, Greek letter epsilon. And each of these are different. Red, green, blue are 3 different energies, okay? And that's what you get for that particular atom. And this is the energy level diagram. And they get closer as you go up. N equals 1, N equals 2, N equals 3, and N equals 4. Now, this is energy here, going upwards. So when the atom is excited, the electron jumps to here, comes back down, gives out that energy. Or it might jump to here, come back down, give out that much energy. Or it might jump to there and come back down and give out that much energy. And of course, they would be the 3 lines then. That's the lowest energy. That's the next lowest energy, and that's the highest energy. And that's the whole criteria which you're writing now. Now that's a template on which you base your remarks, and I'm going to answer the question now. Explain how a line emission spectrum occurs. An atom in the ground state has electrons in the lowest available energy levels, or in the innermost shells. When an atom is excited, its electrons jump to higher energy levels. And that makes the atom unstable. So it will stabilize itself by the electrons coming back down to their original ground state. When they come back down, they give out energy in the form of light. And as it happens, if you looked at that light through a particular device called a spectroscope, you'd see an emission spectrum. And therefore, no two atoms have the same emission spectrum. But that's effectively what they want there. And I realize it's a limited question because a line emission spectrum is the result of that. And the one thing you'd have to say is the energy of one of those lines is epsilon, and it's equal to E2 minus E1, where that is E1 and that is E2. So E2 minus E1 is the size of the jump. That would be E3 minus E1. That's a different line. And that would be E4 minus E1. Okay, so you're talking about the energy of any one line corresponds to a certain jump in that. And that means, of course, the electrons are restricted to very special locations around the nucleus. And that's what Bohr said about it, and that's correct. What evidence do line emission spectrum provide for the existence of energy levels in atoms? Now, you'd have to make a statement here that each energy epsilon is a different color. And no two atoms have the same energy level diagram. Let me just draw, that's an energy level diagram. Let me draw a small one here for you. That's one atom now, energy there increasing upwards. Here's a second atom. So can you see that the first, we'll say that particular jump in each case, the highest one. That's the highest one there, there's the highest one there. So no two of them are the same. No two atoms have the same energy level diagram. So the amount of energy given out from each is different, and therefore you have a different, it depends, and the energy given out as epsilon depends on the frequency of the light, and frequency is another word for color. So each of these little drops here have different colors, and so it's unique to the particular atom in question. The last part of that, why is it possible for line emission spectrum to be used to distinguish between their elements? And you're going to say because each of them gives out a different amount of energy, characteristic of that element, and consequently you are talking about an emission of energy in the form of light. Now, by the way, there's only 3 marks for that last bit. So you'll appreciate the answer has to be in response to the reward. Why is it possible for line emission spectra to be used to distinguish between different elements? Because each element gives out a different colour. There's only 3 marks. Okay, that's part B. And finally, part C, which is a different part of the course again. And I suppose it's good when you get a diverse set of questions because, you know, it's not all from the one pool, and therefore you're likely to have a bit of choice in it. And that's very useful to have that. Now, let me deal with this because I know there are issues involved and we have to try and make out whatever we can of this, but I'm going to just go through it now with you anyway. Part C. Use electronegativity values to predict the type of bonding in phosphorus trichloride, calcium chloride, and carbon dioxide. Now, and they give you, thankfully, they give you the formula for each. Okay, the first one is phosphorus trichloride, PCl3. The second one is calcium chloride, CaCl2. And the next one is carbon dioxide, CO2. Right, and it asks you to use electronegativity values to predict the type of bonding in each of these 3. Now, are you aware, I'm sure you are, that all your electronegativity values, this is page 79, the electronegativity values are on page 70, are on page 81. Okay, ionization energy is page 80, and the one after that, you look it up anyway, you open it in front of you, and you have them there, okay? And they're measured in Pauling, so you'll probably realize that, but you can look them up. So I looked up these values. The value for phosphorus, they tell you now to use electronegativity values 2.19, and chlorine happens to be 3.16. Okay, and down here then, calcium happens to be 1.0, and chlorine happens to be 3.16. Okay, and lastly, carbon happens to be 2.55. and oxygen happens to be 3.44. So the difference for each of them, the difference for the first one is 0.97. The difference in the 2 numbers, 0.97. The difference for the next one is 2.16. And the difference for the third one happens to be 0.89. That's the difference in the electronegativity values between any one of those bonds. Okay, and they're asking you the question, use them to predict the type of bonding. Now, we have a rule. I wonder, do you know it? I haven't this done with you now. You would have done it very early in the year. Would you have it done already? Before I state the rule, do you know what I'm alluding to? If the electronegativity values between two atoms, there's X and Y, and if the electronegativity values differ by 1.7 or more, then that particular bond will be ionic. If it's less than 1.7 or less, if it's less than 1.7, it will be polar covalent. And if the difference is 0 or almost 0, it will be covalent. In other words, if the two atoms pulling for the electrons are equal in strengths, then it will stay exactly in the middle. But if one of these atoms is much stronger than the other, then of course that one will pull the electrons towards it. It will become negative, and it will become delta minus and delta plus. And if the pull is enormous, if it's greater than 1.7, then this guy is going to run off with the pair altogether and it will become ionic. Now, you would need to revise that, obviously, but we're basing our results on this anyway. That would be polar covalent. Polar covalent. Now, let me deal with the question. The question says, use the values, okay, to predict the type of bonding. Now, polar covalent bonding, I'd want you to write down. It's a polar covalent bond, right? And this differs by more than 1.7. This is ionic bond. Okay, and this 1.7, this is polar covalent as well. Very important that you have them like that. That's polar covalent as well. And that's what they want from you, nothing more than that. Nothing more, that's all that was required, okay? But you had to have the ground rule of this magic number. If the pull between one and the other isn't very different, then, you know, the molecule will be polar. If it goes beyond that, then it will be more, and you have to work with that. That's what we have in mind. I'll move on from that because there's another bit here. Distinguish between intramolecular and intermolecular bonds. Okay, intramolecular and intermolecular bonds. The word intra in Latin means, of course, within, and inter means between. We would talk about internationals, between countries. Okay, so inter means between. So the bonds between molecules are called intermolecular bonds, and there's only 3 of them there. Van der Waals, dipole-dipole, or hydrogen bonding. They're intermolecular bonds, and generally speaking, they will determine which of the 2 substances has the higher melting point or boiling point, or which of the 2 substances is more soluble. Now, there's a sound tip for you. If anybody asks you why this compound has a higher boiling point than this, will you take it that the one with the higher boiling point has stronger intermolecular bonds, so they're harder to separate, so they're harder to gasify. And that's exactly what they want, nothing more, nothing less than that. And you'll work with that in mind. I hope that's okay. Right? And that's effectively what you're trying to deal with there. There wouldn't be anything more than that, okay? Solubility, likewise, like will dissolve like. Things dissolve in water because they form hydrogen bonding with the water, like HCl, for example, would bond with water, things like that. So solubility, melting points and boiling points are always intermolecular bonds. Intramolecular bonds are these guys. They're in the bond, okay? You're talking about P and Cl there, P there, Cl there, Cl there. So you didn't need to use this now at all, but that's an intramolecular bond. That's a covalent bond inside the molecule. It's a polar covalent bond as it happens, but it's inside the molecule. So covalent and ionic are generally intramolecular bonds. In particular, covalent ones, put an emphasis on them. Use your knowledge of bonding and molecular shape to suggest why the boiling point of carbon dioxide is significantly lower than the boiling point of water. Now, carbon dioxide and water. This is opening a much bigger issue now. You have to go back and do a lot of revision here, guys, to get up to speed on this. It's a while since you were doing it, and you're bound to be out of touch with it. I'd ask you to do that. Okay? Carbon dioxide is CO2, right? And its boiling point is minus 57 degrees Celsius. That's irrelevant, by the way, other than just giving you a value. And the boiling point of water, H2O, happens to be 100 degrees Celsius. Okay? They're just giving you them. Now, folks, I've already tipped you off. if anybody mentions boiling point to you, a knowledge of boiling, of bonding and molecular shape to suggest this. Of course, in this particular instance, that's effectively what's going to happen. The shape of carbon dioxide is linear. Carbon has a valency of 4 bonds. Oxygen has a valency of 2 bonds. That's probably the most neglected molecule in all the chemistry for leaving cert. There's not much on the course on it at all. But carbon has to form 4 bonds, you can see them, and the oxygen forms 2, so there's double bonds in it. This is more electronegative than that, so delta plus and delta minus. The oxygen is more electronegative than that, delta plus and delta minus. But because it's a linear molecule, the center of the pluses is there, and the center of the 2 minuses is also there. So they cancel each other out, and therefore that particular molecule would be non-polar. Okay, that's very important. Use your knowledge of bonding and molecular shape to suggest the boiling point. So that's a non-polar molecule. I'll be back in it in a moment. It's non-polar. And water, you should know, oxygen has a shape like that. Okay? If you were to describe it further, oxygen has a total of 8 electrons, 2 in the first shell and 6 in the next. And if you drew that then as a nucleus, 2 in the first shell and 6 in the next. 1, 2, 3, 4, double, double. Can you see there's 2 left there then? The hydrogen goes on there. And the hydrogen goes on there sharing. So the 2 sharings go on there. So that's the kind of shape you have. It's a V-shaped structure. Okay. Now take my word for it for the moment. The shape, it's V-shaped. Okay. There's a pair there, a lone pair there and there. Now this would be delta minus and this would be delta plus. This would be delta minus and this would be delta plus. The center of the minuses are here, but the center of the pluses would be along a line here. There. That would be the center of the pluses. So there's a minus end and a plus end to that molecule because it is not linear. So let me just say that again to give you some idea as to what we're dealing with then. If the molecule is linear, then it's likely it's non-polar. Whereas if there's a bend in it, the center of the pluses, the center of the minuses here, the center of the pluses are down here. So consequently, you end up with a plus end and a minus end. There's the minus end, there's the plus end. Okay, and that's what you're trying to deal with there. And they're asking you to use this knowledge of the 2 of them, okay, to signify that. Now, that then has a higher boiling point than that, because the intermolecular bonds between water is hydrogen bonding, which is the strongest intermolecular bond. Whereas the bonding between carbon dioxide is van der Waals, which is the weakest of them. And that's very important that you would have that together just in what you'd be doing. Now, I'm asking you in this instance just to be aware that's a broader picture and it's material you'll need to do again. And you'd have done it very early in your 5th year course, I suspect, and therefore it could be a bit rusty, so you have to go back at it. They need not have given you all that prompting at all there, a knowledge of bonding and molecular shape. They might just say, explain why water has a much higher boiling point than that, and I've tipped you off already. This is a polar molecule, this is non-polar. So this has hydrogen bonding and this one has van der Waals. This is a much stronger intermolecular bond. You'll find it harder to separate the molecules. Therefore, you have to heat it to a much higher temperature to get it to evaporate, to get it to gasify, and therefore a much higher temperature is needed. Now, I'd be hopeful that that's doing okay with you and that you're fine in that. Now, before I finish with you, can I say this to you? In our next video, we'll be starting a new category. It's oxidation and reduction. And I have already supplied notes for this. You'll need to have them printed for the next session. Oxidation and reduction is a new unit. We've nothing done on it already, and I'll have to go through that with you using your notes. It will be very important that you will download them, that you will print them out, and that you'll have them ready for the next video. All right? Okay.